part 4 of Module 2 Solution Chemistry. In this episode, we will be studying acids and bases featuring pH and pOH. At the end of this module, you should be able to define strong acids and bases using Arrhenius theory and Brønsted-Lowry model, define pH and pOH, and finally, perform pH calculations with strong acids and bases. Acids and bases are everywhere. They're used to make foods, soaps and detergents, even explosives. Our stomach is acidic, our blood is basic, and our DNAs are both. Physically, acids and bases could be differentiated through their taste and feeling when touched. Acids are sour, while bases, or also known as alkalis, are bitter. Acids are known to create a burning effect of whatever comes in contact with them. They can, depending on its strength and concentration, erode surfaces or burn the skin. Bases, when added to water, give foam and feel soapy or slippery when touched. The best examples of substances that contain acids include citrus fruits like calamansi, vinegar, and our beloved coffee. The best examples of bases include cleaning materials such as soap and detergent and baking soda. On a molecular level, the rigid definitions of acids and bases could be explained using models. Initially, acids and bases could be defined through the Arrhenius concept. According to this theory, an acid is a substance that has hydrogen in its formula and dissociates in water to yield H3O+ or hydronium ion, which is also equivalent to H+ or hydrogen ion. As shown in the example, HCl, which contains H in its formula, when dissolved to water, dissociates to hydronium ion and chloride ion. This process could be presented as HCl plus H2O yielding H3O+ and Cl-, or simply HCl yielding H+ and Cl-. While bases are substances that have OH in its formula and dissociates in water to yield OH- or hydroxide ion. As demonstrated here, NaOH, when dissolved into water, produces Na+ and OH-. However, these definitions have limitations, such as, even though some substances do not have OH in their formulas, they still behave as bases. And water has to be the solvent of the acid-base reactions to determine if H+ or OH- are produced in the dissolution process. These limitations are overcome by the Brønsted-Lowry model. In this model, an acid is defined as something that donates a proton or any species that donates H+ ion. An H+ ion is a proton because if a hydrogen atom loses an electron, all that is left is a proton that comprises the nucleus. Therefore, an acid must contain H in its formula. Hence, all Arrhenius acids are Brønsted-Lowry acids. Like in this example, HCl is considered as an acid because it can donate its H+ to water, leaving Cl- and forming H3O+. Whereas, a base is a proton acceptor, or any species that accepts H+ ion. Just like in this example, it must contain a lone pair or non-bonding electrons to bind the H+ ion, forming NH4+. This model, however, is limited to protic species. are molecules with hydrogen atoms that can be lost to protons. But there are aprotic species that also display acidity and basicity. This is what the Lewis definition entails. However, that definition is not covered in this module. As a summary of the models presented, Arrhenius and Brønsted-Lowry define acid as H plus producer and H plus donor respectively, while Arrhenius and Brønsted-Lowry define bases as OH minus producer and H plus acceptor respectively. You probably heard of the terms strong and weak acids and bases already, but what exactly do they mean? The strong and weak adjectives are added to acids and bases to classify their relative strengths qualitatively. Strong acids dissociate completely into ions in water, so they dump their protons more easily to water. Generally, the process could be represented as HA plus H2O yielding hydronium ion and the anion A-, or simply HA dissociating to H plus and A-. Most common strong acids include hydrohalic acids, which are acids of halogens, and oxoacids in which the number of O atoms exceed the number of hydrogen by 2 or more. For example, HClO4 or perchloric acid. It has hydrogen of 1 and 4 oxygen atoms. Others are nitric acid and sulfuric acid. While weak acids dissociate very slightly into ions in water. These acids donate just a few of their protons to water, represented by this equation where the hydronium ion and anion could react again to form the corresponding acid in water. In this module, we will only deal with strong acids. Similarly, strong bases dissociate completely into ions in water, forming cation and hydroxide ion. As seen from this general equation, most common strong bases include group 1A and 2A oxides and hydroxides, which are represented in these general formulas. In contrast, weak bases dissociate very slightly into ions in water, where the products would react again to form the initial reactants. Likewise, in this module, only strong bases will be discussed. Now, given a substance, we cannot, however, determine its nature, if it's an acid or a base, or classify its strength by tasting it to categorize it as sour or bitter, nor we cannot drop the substance on our skin to feel if it's burning or soapy. To accomplish this, we introduce the concept of pH and POH. pH is short for power of hydrogen. This is because hydrogen ions are pivotal to the behavior of acids and bases, which is what pH describes. So basically, pH is the measure of the strength of the acid or base character of a substance. You'd probably be thinking that if pH only considers the concentration of H plus ions, how can it tell us how strong a base is? Recall that bases also contains H plus ions from water, just that the concentration of H plus ions is far lower than that of the concentration of OH minus ions, so low that they are practically disregarded. Mathematically, the pH of a solution is represented as the negative logarithm of H plus or negative log of H3O plus ions, in which the square brackets tell that the concentration should be expressed in molarity. The number of decimal places of pH is equal to the number of significant figures in the concentration of hydronium ion. pH is generally a number from 0 to 14, where the lower the pH value, the higher the hydrogen concentration. Therefore, acidic solutions have lower pH. The figure on the right depicts a pH scale where common acids and bases are identified. More acidic solutions have lower pH, such as 1 molar of HCl. A pH of 7 is theoretically considered neutral, where the concentration of H plus and OH minus are the same. Finally, higher pH values greater than 7 represents the basic solutions. To conveniently describe and measure the basic character of the solution, we use pOH. pOH, likewise, is the power of OH and is represented mathematically as pOH equals negative log of OH minus ions. In relation to pH, pOH when added to the solution's pH is equal to 14, which means that at low pH, where the concentration of H plus is high, the concentration of OH minus is low. Therefore, the solution is acidic. As an example, what is the pH of an HCl solution with a molarity of 1.5 times 10 raised to negative 4? Recall that to calculate the pH, one must know the hydrogen ion concentration. Let us represent the problem using an equation. Note that HCl is a hydrohalic acid, which is a strong acid. Therefore, it simply dissociates to H plus and Cl minus. We can use the equation to determine the amount of H plus stoichiometrically. With that, we would need to have either the mass or moles of HCl. We can do that by having a basis of 1 liter of solution. Consequently, by multiplying 1 liter of solution with a given molarity, we would get 1.5 times 10 raised to negative 4 moles of HCl. Now, we can get the number of moles of H plus ions by multiplying the known amount of HCl by the coefficients of H plus and HCl, which would be 1.5 times 10 raised to negative 4 moles of H plus. To get the molarity, divide it by the volume of the solution in liters, which is 1 liter, and get the corresponding pH, which is 3.82. In the laboratory, pH could be measured by titration, which also entails manual calculations, using pH indicators, usually in paper, and pH meter that digitally represents the pH of the solution. Indicators are substances that indicate the presence and/or concentration of H3O plus ion in a solution via color change. These are some of the common types of indicators. First, natural indicators. As the name suggests, these indicators are obtained from natural sources. One of the oldest forms of pH indicator is litmus paper. It is derived from lichens, which are composite organisms that arise from algae or cyanobacteria living among filaments of multiple fungi species. If you remember, an acid turns blue litmus paper to red, while a base turns red litmus paper to blue. Another natural indicator is a red cabbage. It is red, pink, or magenta in acids pH less than 7, purple in neutral solutions of pH equals 7, and ranges from blue to green to yellow in basic solution, or pH greater than 7. Substances would change their smell when mixed with acid or bases are called olfactory indicators. Examples are onion and vanilla. Both of them loses and changes their smell when added with base and doesn't change when added with acid. These indicators are helpful for visually impaired individuals, especially in the lab. Finally, there are synthetic indicators, which are those synthesized in the laboratory. Phenolphthalein or phenolphthalein is a colorless liquid and remains colorless with acid, but turns pink with a base. If you noticed, most indicators only tell us the acidic or basic character of a solution. but it doesn't tell us the strength. With universal indicators, the strength of acid or base could be identified. A universal indicator is comprised of various indicators that shows different colors over the range of pH values from 1 to 14. For every color, there is a corresponding value for pH. Those in the shades of red are acids, while those pH greater than 7 are blue to violet in color. Wear your thinking cap and prepare your calculator, pen, and paper. Let's go! Are you ready? Are you sure you're ready? These are the self-assessment questions. You may find a copy of these questions in the handouts provided by your instructors. Write your solutions and the Tomasian honor code in clean sheets of paper. Scan or take clear photographs of your papers and upload in the corresponding submission bins provided by your instructors. This is the end of Module 2.4 and Module 2. If you have questions or clarifications regarding the topic and the SAQs, feel free to contact your respective instructors. Thank you for listening and have an amazing day.